Okay, yeah. So basically the overview is that for convolutional neural networks, what we're doing is we're taking a convolutional network that normally goes to a fully connected layer, and we instead we use a decision tree or a random forest instead of the fully connected layer. And then afterward, what they're doing is that they're retraining a neural network to try to replicate what the random forest is doing.
Hmm.
And so the two main questions is, why are we using a random forest instead of just using a fully connected layer in order to try to work with classification of problems? And then the second one is, why are we even like converting back to a neural network? Like if we're going to use a random forest, why are we converting back into a neural network? And so what I did is I took data. I just did a little basic exploration where I took the ISIS, or not ISIS, the Iris. I don't know. There's like this one data set from Kaggle. I used LDA and converted it into just a two-dimensional data where it's very clear what these classifications are, or like it looks pretty clean. And this is a random forest approach. And this is the neural network approach, where it looks like it's okay, but the neural network is clearly like, if you were to put it over here, it starts at negative 2.5 and goes to 0. So it cuts really close to the yellow. And this is mainly because neural networks, they're very flexible, and they have like, they can only learn based on these training data. And so there's no built-in structure that a random forest has. And this is the main reason why the classical like statistical models work or generalize a lot better with a lot less data than neural networks do. And that's kind of the main reason why they've decided to use random forest, is if you're trying to do image classification, but you're trying to do, for example, like a rare animal, or trying to differentiate between different like rare animals, and you don't have a lot of data with it, it's kind of like alongside the same thing as like one-shot learning, where you're trying to learn as fast as possible and generalize as well as possible on as little data as possible. So that's kind of the main reason why random forest is used. And I'll get to this later. How do I share?
Is this only us? Can I ask a question already, or do I have to? Should I wait until the end?
Actually, yeah. Let's. Do you have any questions?
Yeah, I actually. Can you go back to the previous slide? I just want to understand more what happened there. So I understand why is it been more beneficial. Yeah, here. What's going on here? I'm sorry, I just didn't catch it.
Okay. So, this is basically just, I have this data right here, and I trained a random forest model and a neural network to predict the class based on this.
Okay.
And then what I did was I generated like not random data, but like I basically mapped out the decision boundaries using matplotlib. So this is predicting red, this is predicting red, this is predicting.
Oh, I see. Okay, I see. So this is the region where it will assume this data will be blue or red or yellow.
Yes.
In the plot. Okay, I see.
And
So Alex,
yes.
yeah. So Alex, one question only. Like in these diagram which I see, like you are using three classes, right? And random forest give you the better decision boundary result and classify these classes in more efficient way as compared to the neural network. Is that the slide showing in this particular diagram?
Yeah, the class of like, I kind of have to go off of people's words. I didn't want to spend too much time on this, but random forest is significantly better with less data than neural networks are. And so the basic idea is, because the way that random forests work or decision trees work is that there's kind of some inherent structure to its prediction, and neural networks is kind of just like randomly generated, and then it kind of just like smooth things around or move things around until it gets a good prediction. So
if your data is large, then random forest performance might degrade, and neural network might be a better option in that scenario.
Neural networks might be better. It kind
if you
of
have a larger data set.
I don't really know much.
Okay, no worries.
Yeah, the way it normally goes is that like support vector machines are by far the best with very minimal data in terms of generalizing to new data, and then it goes
Okay.
like decision trees or random forests, and then neural networks. So I would assume that neural networks may perform better, but you have to do a lot of regularization techniques that you don't really have to do with random forests. So I don't know, even with like a lot of data,
Yeah.
it might be better, but like because you would also need robust data and like
Right.
that has like very like wide high variance, and so that you could stretch it out so that neural networks would probably perform similar to random forests.
Okay.
But like
Okay.
yeah, because this is very sparse, and random
Right.
forest is able to just like quickly like create
Right.
model, and neural networks kind of like smooth things around, and like if it works, it works, and like there's no difference for a neural network between this and this essentially, but like for some reason it always chose this.
Right.
Mm-hmm. Makes sense.
Although like there's also like the whole like what is it, the no free lunch theorem or whatever, where it basically says you never know which model is actually going to work the best until you try every single one, or you try the different models, because like that specific data, although it doesn't necessarily mean that it'll generalize all the way through, generalize better, but different models perform better. It depends on the structure of the data. Let's see. Am I on the right? I believe I'm on the. No, I'm not. Okay. Okay. And so I believe I've kind of answered the first part where we're trying to figure out why we're using a random forest, but then the main question, like why we even bother like converting it into a back control neural network, is mainly because of like the processing speed. We want to be able to get these classifications as fast as possible, and a neural network, it's just like it's one pass through with the neurons, but for with a random forest, it's like 100 different decision trees, and so it's much faster. And if you have to do it really quickly, then being it, or it's like on a mobile device or something like that, then it's much easier to just have a quick neural network go through. Could you mute your mic? This is a little bit of a background. Okay, thank you. So let's see, advantages random forest. Like that's kind of like all just like an intro for this paper. They kind of take it for granted that just statistical models generalize better with little data when compared to neural networks, and they kind of take it for granted that you want to retrain a neural network to try to copy a random forest. And this is more of just a little bit more advanced, where they've come up with a new way in order to create a neural network that mimics the random forest. And traditional models, I'll kind of go a little bit lower, but traditional models, normally what they do is like there's a way to just brute force it, where you take a decision tree, and then you take a neural network, and for each like decision or each like little like separation, you have like a node. And so there's basically a way to like brute force a random forest decision. And what the main problem with that is just the number of parameters that you end up doing. The network actually becomes really big. And what they're trying to do is they're trying to come up with a way to train a neural network so that you don't need as big of a network. Because that's mainly the whole point of training a neural network on random forest, is to get the generalization of a random forest, but also maintain or like increase the speed. And that's kind of just like the different like sizes. Sometimes it gets really big. Like these are really big compared to the model that they were able to create in terms of how many parameters you have. And this is kind of background, but the main approach of what they do is, instead of using this algorithm to create the neural network, they do this like they basically just generate data where they want to create they choose a specific class. They choose one of the leaf nodes that correlate to the class, and then they work backwards all the way to the back, and then they have a certain mean and standard deviation that they choose from, and they multiply it by a factor, a parameter, to increase the standard deviation to increase the distribution in order to help improve the neural network. And then they train the neural network on the data, and they keep generating data as they go, and they train the neural network. Let's see. And this is kind of just talking about the different, they tried multiple different approaches. I can't really remember specifically what the difference is, but they have mainly 3 different approaches. And then here's the baseline. The dotted line is the accuracy of the random forest on the set. And then this is the accuracy of the neural network. And they're mapping just what network size you need in order to be able to get the optimal accuracy. Because since this is generated data, you can't really get accuracy higher than the accuracy of the random forest, because it's relying on the random forest in order to get accuracy. Or you're basically relying on the random forest to get the data. And so this is kind of just the measuring accuracy. I don't actually know how they get higher accuracy in the test set. I think it's just lucky, to be honest. But that way, I didn't even notice this one. Oh my god. Okay, but yeah, that's interesting. That one of the neural networks happened to perform better than the.
Alex, I posted a question on Zoom. Could you just have a look at that?
Oh, sure.
I'll just keep my mic on mute.
I think it's pretty relative. Like they tried this method on something that's 60,000. Like it's pretty relative, and I don't really know. So like, I guess like take whatever I say with a grain of salt. I think I remember hearing somewhere where it's like for classification or like for pretty good, like pretty broad, I guess you want something like 10,000 for labels and for the CNN, or like that's like the ideal. Oh, like that could be, it might have been, I don't think it's 1,000. I think it was 10,000 was like, is really good. But yeah, there's no real clear like delineation. I think it also depends on the problem. If it's something that's really easy to figure out, like cat versus dog, it's only 2. I think actually no, the cat versus dog is pretty difficult because they both look fairly similar. If it's like an easy classification task, then it won't take as nearly as much. And you might as well just try the different methods regardless.
Yeah, I think if you go to the accuracy graph, C400 has larger data set and larger classes. That might be the cue that this approach works for a limited amount of data. C410 with C400. C410 is like subset of C400.
Okay.
MNIST, we know it's only 9 classes with 60,000. But I think C400 would have many more classes and larger image sizes in. So that might be the cue that probably give us an idea what exactly would be the nice data set number to use this method. That's just the thought.
I don't know. I can't imagine having 10,000 images per label, but it looks like they just said like this is 60,000, which I guess is less than 10,000, but this is like 14 million. Although it does have a lot of classes. Yeah, I mean the accuracy itself is 40%, so it's pretty abysmal even with like just in general. The rest of these accuracies are pretty good. So that honestly might be part of the thing is like just with a small, like the accuracy is so bad that there's higher variance. So that might be what it is. But and here they're just measuring how robust the neural network is when compared to the random forest, just to see like, does it just fall off or is it Good. Yeah. I'll be honest, this paper was not as interesting as I thought it would be.
But can you please tell us what do you mean in the last part?
This part?
Yeah.
Looks like they're comparing it to the maximum decision tree depth. Oh, this is just the okay, it's the network size when compared to the tree depth. Looks like there's a looks like it's kind of a drop off somewhat. So they're trying to measure like the bigger the decision tree depth. One of the one of the problems that they were running into with the original method, where you're trying to just hard code the neural network to mimic exactly a random forest, is you can only do specific depths. So, like basically, because you have to do every single node, whenever you increase a depth, you're basically like exponentially increasing the number of nodes that you have to be able to mimic with a neural network, and so you get an explosion in the amount of parameters. So this is what they're saying right here, is like with their method, even though you're increasing the decision tree depth, you're not actually increasing the number of parameters of the network size by that much. It's showing that like it's able to mimic the random forest without exploding in size.
It's actually interesting as well to look how they managed to do this. I think this part is interesting.
Yeah, that's actually really surprising to be honest. Although I guess like the bigger or the deeper you allow a decision tree, there's only so much that it can like increase in complexity maybe. And so there's a lot of like, I guess, fake complexity that gets eliminated when you train this way. But the main advantages of using their proposed method when compared to the standard one that was kind of just pushed out probably last year or a couple of years ago is just the network size itself is significantly smaller, but the actual accuracy, there's no real drop off in accuracy.